as we continue to build our OSPF networks, we have full connectivity. We have two more routers to get to. One is R3 and the other is R4. So let's take a look at our tasks, see how specific they are, and then go to the configuration. So on R3, we're going to use network statements matching on the first octet. So we want to include all the networks, put them into area 0 for OSPF, and match on the first octet. So what that means is we're going to use a wildcard mask of 0, meaning we care about that first octet, and then 255.255.255 for the last three. And then we'll have to take a look at the IP addressing on R3 to make sure we include all of its interfaces and match on that first octet, whatever they are. So we might have to add several statements to do it. Let's go ahead and take a look at R3 right now. So from our management computer, we've opened up a session to R3, and let's do a show IP interface brief, see what we're dealing with here. So it's got 1, 2, 3, 4, 5 interfaces, okay? And if we do a show IP route, press enter, and there's the routing table. So if we peek back at our task on R3, use network statements matching on the first octet, let's go ahead and see how few network statements we can do if we're going to match on the first octet. So I'm going to hit the up arrow key a couple times for show IP interface brief, and it looks like we could just get away with 2. So if we're going to match on the first octet, we could match on 10, and that would get gig 0010, and also get serial 3/3 and fast Ethernet 4/0. And then we could have a separate network statement that matches on 3. So we could do this with 2 network statements using a 3-octet wildcard bits on in the mask. So let's do it. We'll go into configuration mode, router, OSPF 1, and then we'll specify a network space, and we'll do 10 dot, and we'll put the last 3 octets to 0. And then for the wildcard mask, we'll say we care about matching on the 10, but we don't care about matching on the 2nd octet, the 3rd octet, or the 4th octet. Then space, the keyword area, and then the area we want any matching networks to go into. And we'll press enter. I thought the word 0. I thought the number 0. I just didn't press 0. There we go. Area 0 and press enter. All right. So now we've got 1, 2, 3, 4 interfaces and their respective networks participating in OSPF. Let's go ahead and get the loop back as well. So we'll simply type in network space 3.0.0.0 because the request said only match on the first octet, and we'll say 0.255.255.255 and then area 0 and press enter. And you'll notice we also got a couple messages in. We got a message from a neighbor at router ID 2222 and also 1111 saying, hey, welcome to the neighborhood. Let's share information. So let's type in end, and let's take a look at our topology. So in our topology here, we've configured R1, R2, R3, and the task list didn't say anything about configuring R4. But because we want full connectivity, we had to do it as well. So it's up to you. In the lab, you can configure the network statement any way you want to. You can use exact matches, as we did on R2. You can use a wildcard mask of 32 bits to say include everything. Totally up to you. So let's go to R4 and bring R4 into the fold as well and have him run OSPF. So here on R4, let's do a config T and router OSPF 1. In fact, let's take a look at the interfaces. Do show IP interface brief to see what we're dealing with. And let's do a wildcard for all of them. So here in router configuration mode, let's use a network statement, and we'll put in 0000 space with a wildcard of 255.255.255.255. Then we'll follow it with area space and 0. Now, I want to tell you about something interesting and a little bit scary. Imagine that we use the network statement. Let me back this off. If we use the network statement like 1.2.3.5, and then we did a wildcard mask of this. In theory, what that should do is that should say, oh, the wildcard mask doesn't care about any of these bits. It doesn't care about the bits in the first octet, 2nd octet, anything. It shouldn't matter at all what those are. However, in some flavors of iOS, if you do put a value here, and then you put a wildcard mask of all bits on, the operating system on some flavors of iOS believes that you intended to actually really include and only match on 1, 2, 3, 4, 5, and it will actually flip all of these bits to zeros in the configuration. So what you want to do is, if you really want to match on everything, we want to put right here all zeros, and that way the operating system isn't going to try to help you correct it. So we're going to put in network 0000 space, and then we're going to specify the wildcard mask of 255.255.255.255, and then area 0. And then we'll do a do show IP OSPF interface brief. And what we should have is all of our interfaces included inside of OSPF. So we have 1, 2, 3, 4 interfaces, and sure enough, they're all participating as part of OSPF. And we got messages indicating that we're communicating with some good buddies who are also other routers who are also running OSPF. And so now, with all that done, if we type in end, if we do a show IP route, and then we limit the output just to OSPF learned routes, let's do that. Show IP route OSPF, press enter. Look at this. We have a whole bunch of OSPF learned routes. So up here in the decoder, here it says capital O is for OSPF, and this O right here represents that they are learned via OSPF. And we have routes to the loopback addresses. We have routes to the 10.2, 10.3, 10.12, 10.13, and 10.23 networks. And in some cases, we have parallel paths. We have more than one path that OSPF at this point believes are both equal cost paths, and it can use both of them. So the commands, in addition to configuring OSPF, the commands that I would encourage you to test and try would be show IP OSPF, and show IP OSPF interface, and show IP OSPF interface brief. And what I'm doing is I'm doing a Control-C so that you can see them and practice with them. And now that we have other OSPF speakers, other routers that we're communicating with, we could also do show IP OSPF neighbors. And if I press enter on that one to go ahead and see the output, it's showing us from R4's perspective, it's got a neighbor with a router ID of 3333 and a neighbor with a router ID of 2222 who now have the ability to communicate and share route information back and forth between themselves and R4. Now, I would like you to have some fun and practice with this lab and look at the routes, but there's a little teaser that I'd like to throw in anticipation for our very next video about OSPF, and that is why? Why did OSPF choose this path and not that path? Let me show you what I'm talking about. So from R4's perspective, if we looked at the routing table and said, hey, how do you get over here to the 10.3 network? What's the best way to go? If this is fast Ethernet that has a lower speed, it should pick this path right here, which is high-speed gigabit all the way around instead of going this way. but if we look at the routing table on router 4 and we say, hey, how do you get to the 10.3 network? The results are going to be surprising. Let's take a look. And it's still on the screen, so we don't have to go too far. This is a show IP route, and it's saying that to get to the 10.3 network right here, this bad boy, that what it's going to use is fast Ethernet 4/1, which I can tell you is not the optimal path. So another big part of our OSPF task is verify optimal paths through the network. And so in the very next video, what I'm going to do is I'm going to share with you why OSPF, although it is running and we have OSPF adjacencies, we're talking to other OSPF routers, why it's not making the best choice. And this is really important because what we just experienced in the lab is what's going to happen in a production environment unless we make a couple other tweaks, which I'll share with you in the very next video. So I'll see you there in a few minutes. Meanwhile, I hope this has been informative for you, and I'd like to thank you for viewing.